This rational function looks just like all the other ones we've done so far, except for the problem that when we factor this, we'll notice that there's a common factor in the numerator and the denominator of x minus 1, which can be canceled off. And the reduced function of x plus 4 over x minus 5, if you were to graph this on your graphing calculator, and you were to graph this on your graphing calculator, they would look pretty much identical. The difference would be that on this function, if you were to zoom in very close to where x was equal to 1, you would see a small hole in the graph, because I cannot plug 1 into this. So what we're going to do is look at that reduced function, apply all of the graphing techniques that we know to the reduced function, but then we're going to kind of pinpoint where that hole is and draw a little hole in there. So let's go ahead and start by we'll look at the reduced function and graph it. We know that the vertical asymptote is going to be at any x value that would cause a division by 0. So we know that happens when x equals 5. I'm going to write x equals 5 to have the equation of a vertical line, and I'm going to draw on that vertical line. To determine the horizontal asymptote, I'm going to look at what the lead terms are doing. So this lead term is x. That will take over for large x's. This takes over for large x's. X over x reduces down to 1. So the horizontal asymptote would be at y equals 1. And I'm going to be a little careful here. Oh no, for the x-intercept, I'm going to look at that reduced function. The x-intercept is whatever makes the numerator 0, because that would make y equal 0. That happens at -4. That's here. And the y-intercept is what I would get were I to plug in 0 for x. And if I were to plug in 0 for x, I'd be left with this expression, 4 over -5, which of course equals -0.8. So I would like to just go ahead and connect all these dots, but I have a problem, and the problem is that this function is not exactly what I'm graphing. I'm graphing this function, which is this function, with x not equal to 1. X can't equal 1. So what I want to do is figure out, well, if I could plug 1 into here, what would it look like? Like, what would the y value be? So to figure out what the y value would be, if I could, I'll plug that 1 into here. And that will cause a division by 0, so it's going to be an okay value. But the difference is, instead of putting a dot to say this is where it is, I'm going to put an open circle to say it can't go here. Everything around it will be fine, but there, can't go there. Don't go there. So let's take that 1, let's plug it into the reduced function. Let's see, here's how you find the hole. The hole is when x equals 1, which would imply that y would equal whatever 1 plus 4 over 1 minus 5 is. And that is, of course, 5 over -4, which is -1.25. So I have a hole at 1, -1.25, which is here. I'm going to draw an open circle, just like that. Now, my grid, my graph, has to go through all points, and it also has to hit this hole. That's what has to happen. Do this in blue. So I've got to approach this asymptote. I've got to go through this doorway. I've got to go through this doorway, and I've got to act like I'm going through there, but I'm not going to actually go through there. Pretend that I hit that point. And as I approach the asymptote, down I go. And on this region, this side of the vertical asymptote, I've got to approach this asymptote, and as I approach the vertical line, I have a choice of veering up or down. But if I veer down, I've got to cross the x-axis, and there's no intercept there, so it's going to go up instead. And that's basically it. If you have a hole, that happens when you had a common factor that cut out, that got canceled out. That tells you there's an x value that you're not allowed to use. But you can take that not allowable x value and plug it into the reduced function to find an appropriate y value and plot a hole at that point. Good luck.